Hey everyone, thanks for joining. Thanks for joining. And welcome to Creative Coding with Compose. Just a little bit about myself and why I wanted to give this talk. So my name is Tasha, and I work at Tinder. And about a year ago, I started to get into creative coding and wanted to explore how those ideas would translate over into the world of Compose. Unfortunately, my co-speaker, Spooky, couldn't be with me today because she had other speaking arrangements, but she's a great creative coder and helped me with my slides. So, sometime last year, I came across this amazing YouTube channel called The Coding Train, where the host, Daniel Shipman, does these incredible tutorials on implementing really interesting algorithms and visualizations of biological, genetic algorithms, and crazy things like that, with a little bit of graphics programming sprinkled in. And a lot of this work is done in the processing environment, which I'll talk about a little bit later. This was my first introduction to creative coding, and soon after I came across this amazing course on Front-End Masters by Matt Delorier, but this time it was about creative coding on the web using Web Canvas and WebGL. Creative coding is where you code with the intention of creating something expressive rather than functional. And Matt's work was definitely expressive. In that course, he walked us through some amazing examples and also shared some of his art. And here's some of Matt's work. This is from his Instagram. So Matt does a lot of his work in JavaScript. And sometimes he translates these works that are in JavaScript to print as well. And the top is getting cut off a little bit, but this is another artist that uses the R programming language to create generative art. Her name is Katharina Brunner. And I kind of came across a lot of these generative artists, and they were using code to create some amazing things. So that got me super interested in learning more about how people use code to produce such things, and I ended up falling into a bit of a rabbit hole with generative art. I was talking about coming across the coding train and coming across Matt Delorier's amazing creative coding course. So moving on, we were looking at some of Matt's work, and then we were also looking at some of Katharina Brunner's work in creative art and creative coding and generative art. And when we had the weird aspect ratio stuff going on, we were talking about what generative art actually is. So generative art is the idea where you take forms and you draw simple forms and you combine that with some crazy mathematical functions to create some interesting variations. And these give rise to what I like to think of as algorithms, or algorithms that produce art. And these ideas have a lot of applications in games, graphics, big data visualization, and even audio reactive visuals, like things that you see in a concert where you have light shows that play in time to the music. And these concepts can lead to a lot of experimentation and exploration. And you're able to endlessly tweak things to your heart's content and produce outcomes that you wouldn't normally be able to produce with traditional art tools. So the common tools in the world of creative coding, the main tool is the processing environment, and it is a Java-based environment, which kind of looks like super high-level Java, and here's a screenshot on the right. And you basically write this high-level Java-looking code that describes your drawing operations, and then processing creates an app that renders all that to the screen. There's also OpenRender if you're interested in doing the same thing in Kotlin. OpenRender is available for the desktop. There's P5.js and 3.js on web. And a lot of creative coders and generative artists also use OpenGL shaders to write some crazy shader programs. So looking at all these tools, I tried out a few of them, and after going through them a little bit, I wanted to see how it would be to translate some ideas into Compose. And Compose makes graphics declarative, as you might have seen if you attended Nicole's talk right before mine. Yay. And the graphics APIs in Compose are way less cumbersome than their Android View counterparts. So on the right here are some examples of things produced completely in Compose. Some of these were ideas that were originally done in processing and then ported over to Compose, but then others were just fully kind of realized in Compose. So speaking of the stuff that you just saw, you might have noticed that a lot of those things were grid-based. So grids are a very useful starting point for a lot of generative art because you can really build upon a grid in many ways and tweak the way your grid looks or tweak each item in the grid in different ways to produce endless variations, and some of which might be interesting enough for you to curate or consider art. Also, you can begin with a grid and then later move on and break away from the grid shape and do other crazy things. Grids are also simple enough to serve as a vehicle to talk about some basic concepts in generative art. And the general formula here will be you draw the form and then you morph the form over time with mathematical functions. And so we'll explore some tools along the way, some utilities and things that should hopefully be applicable to other creative coding endeavors as well. All right. Oh, skipped too much. So to get kind of situated in our drawing area, and sorry for the weird skew, but again, if you attend Nicole's talk, you know about Canvas, you know how to draw things. So here's a quick map of where we are. Our top left is the 0, 0 coordinate, and our bottom right is as wide and as high as our viewport can go. There are two ways to kind of draw things on the screen. And one way is to basically use your canvas and the onDraw function, and then the other way is to use the box composable and a draw behind modifier. And in both cases, you will end up with a draw scope that you can run your drawing commands in. And here, this is just going to draw a circle with no center specified. And this means that the draw scope has a variable called center. So if you don't specify a center when you're drawing a circle, it'll automatically place your center in the middle of your viewport. So to start drawing a grid, we can maybe do things with 2 nested for loops and get our xy coordinates that way, and start drawing circles at each xy coordinate depending on how many dots we want in our grid. And one thing that I want to point out here is that when you start creating all sorts of drawing commands like this, it's useful to split out your drawing functions as extensions on draw scope, so you can really organize things properly and you can prevent your drawing functions from getting too crazy. Now, if we wanted to kind of take this grid and nicely lay it out uniformly across our viewport, we'll have to do something that we don't typically do when drawing things usually on the canvas. So there's a technique to create a uniform grid, and that technique involves creating a normalized space for your grid points to live in. And what that is basically is you're just taking your viewport and you're chopping it up into the number of grids, or the number of dots you want to show, and what you get at the end of it is each dot is a value between 0 and 1. So this kind of representation is commonly known as the UV space, where each coordinate is not an x and a y. It's a u and a v, where u and v go from 0 to 1. This is also known as the normalized space. So if we just chop up our viewport, get the coordinates for our normalized space, we can then sort of transfer that over into our xy coordinate space and actually render the grids on screen. And for that, we will need to create an offset based on this normalized space that our canvas can understand. So in order to convert something that falls within a 0 to 1 range and a complete different range, we have to talk about linear interpolation, or LERP as it is commonly known. And this kind of utility, or this function, is just for converting values that fall within 0, 1, and to convert them to fall within a different range that you can specify. And we can use this to convert our dots from the UV space to the XY space. So if we start using LERP here, we can kind of start to layer points across the grid. And what we're doing is we're taking the U and the V and LERPing them between 0 and the width and the height. Width for the X, height for the Y. And this enables us to kind of translate those UV coordinates into XY coordinates. And now we can start doing something more. We can start adding some padding around the edges so that we don't have dots sticking to the edge. And this is kind of trivial. You can tack on, a modifier, a padding modifier to your canvas or your viewport, whatever you're using. So one of the first things that we can start morphing with our grid is the size of these dots. Using our UV coordinates, we can kind of change the way the dot sizes look based on where the dots are in the grid. So one of the first kind of transformations you could do is, and that R is cut off there, but that's supposed to say radius. One of the first things you can do is you can take your U, and then you can lerp that between two values, and now you'll have dot sizes that change from the left to the right of your grid. You can do the same thing with V and have the same thing happen vertically. So your dot sizes are now changing from top to bottom. If you combine U and V, you're going to have dot sizes changing at the diagonal. So this can be kind of like a launch pad for further variations once you understand how to play around with this. This is kind of the simplest way you can get started. And this pattern is commonly known as a halftone, which is a 20th century printing technique in which patterns and gradients are represented using small resolutions or small points. So if you wanted to influence our dots with something more interesting, we can look towards our trig functions, sine and cosine. And these are great for creating wavy, repetitive patterns because sine and cosine are periodic by nature. They vary between -1 and 1. So they can be a perfect sort of candidate to transform our grid with. But, like I said, sine and cosine vary between -1 and 1, which means that we have to find a way to map the values that these functions produce into values that our offsets can understand. And that's going to take us to the inverse of the lerp function, or the reverse, called norm, or normalization, or normalize. So lerp was a function that you could use to convert a value that fell between 0 and 1 to a different range. Norm is the opposite. You have a value in some range, and you want to convert it into a value that falls between 0 and 1. And the reason I bring up norm is because if you combine lerp and its inverse, you get a very powerful utility called the map function. And this function is where if you have a value that falls within a certain range, you can express it as a value that falls within a completely different range. And this idea can be really powerful because now all of a sudden you can take inputs that are coming from anywhere, as long as you know what range they fall in, you can express them as positions or sizes and things that you can draw with. And here's a little bit of a pseudocode type thing that kind of goes over how lerp and norm fit together to create the map idea. Now that we know map, we can kind of try to apply that to our trig functions and then map the output values of my screensaver. Okay, all right, we're gonna map our trig functions now. Okay, let's add more variation. So we have sine and cosine going from -1 to 1, and we want to maybe map it to some custom range. So let's see what we can do here. One example is change our radius with a sine function. So here we're just plugging in the value of the u coordinate into our sine function. We're multiplying by pi. You can multiply by any coefficient. And we have something from -1 to 1, and we want to map it to something that goes from 5 to 15 pixels or whatever. You can also change the y offset a little bit. So take the y offset you already have and then shift it a little bit, again using your sine function and the map. And this time we're just shifting by between -10 and 100 pixels. So if you change the number of dots that are in your grid with a function like this, you can start seeing some trippy, wavy patterns. And now you can also bring cosine in to the mix. And here we have cosine and sine that have the same coefficients. And again, depending on how many dots are in your grid, you can start to see some even more interesting variations. All right, so before we go any further or make more variations, let's talk a little bit about how we can capture some of this work. So a lot of this work is kind of just running in a small scaffolding app, and what I usually like to do is have sliders and little buttons and things that allow me to tweak values that can produce some interesting outcomes. But it got really tedious to kind of take screenshots, crop them, and then share it to people or save it or things like that. And I was kind of looking for a way in which I could just capture the relevant portion of the composable with the padding and everything included. And that brought me to a function starting in API 28 called pixel copy. So pixel copy allows you to copy pixels from a given rect in your window into a bitmap. And what you need to use pixel copy is basically you'll need to create a bitmap that's the same width and height as the thing that you're trying to capture. And then you also need to figure out where that thing lies in the context of your whole window. And once you have those two pieces of information, you can tell the pixel copy request to copy the pixels in that rect into the bitmap of that size. And if pixel copy is successful, you'll have a bitmap in hand that you can then share or save or do whatever you want. If you're working below API 28, I believe you will have to wrap your composable in a view and then you use the draw to bitmap function on a view. So it gets a little bit tedious. So to get the data you need to kind of construct this pixel copy request, one of the ways you can do this is to use the onGlobally position modifier. And what this gives you is a layout coordinates object. And this way you'll be able to access the size of your composable, so you can use that to construct your bitmap. And then you also get the layout coordinates, the bounds of your composable in the window. So you'll know exactly where your composable sits in the window. A small caveat here is that if you have stuff drawn on top of the area that you're trying to capture, it's going to capture that too. All right, so with this idea in place, one thing I started doing was just adding a little button in this scaffolding app that runs this pixel copy request when I click it. So if I tweak some value and I find something interesting, I'll just click that and it will copy the pixels into a bitmap, copy the composable, and then I usually maybe open an intent to share it or save it. And if you hit this button in the middle of an animation, it's going to try its best to capture whatever frame was running when you tapped it. Speaking of animations, now, hopefully this is the more fun part of the talk. Let's try messing up our grids a bit more and getting a little crazy. Now, all we've done so far is a static canvas. Nothing's been moving around. We haven't talked about state yet. And we're not really doing anything to move our grid around or anything like that. If we look at the processing environment, processing basically has a function called draw that you override. And this function just continuously runs in a loop pretty much every frame, which means that if you start incrementing values in the draw function, it's going to naturally create an animation over consecutive draw calls. And this draw loop idea is really powerful because it can simplify a lot of animations. And you don't have to think about things individually animating. As long as your canvas is constantly refreshing, you can tweak values and see more screensavers. I'm a space nerd, in case you didn't know. Draw loops. And so this is how processing kind of handles animations. It's just one big draw loop, and you can just change values and things just animate. So I was interested to see how we could translate this idea into Compose. So this is a typical oscillation animation. It's just the Y position of this circle that's changing with a sine function. On the top is a very simplified version of the processing code required to render this. And at the bottom is kind of the ideal that I was trying to look at, a way in which we could replicate this draw loop idea and have our drawing commands kind of be very similar to what you would do in processing. Hopefully this would make things easier to perform animations or like do things where you're porting code over from processing into Compose. So I created a small utility called Sketch. And the reason I use the word sketch is because processing projects are called sketches. So when you run a processing thing, you're running a sketch. And what this function is really, under the hood, it's just an animation state that's constantly being incremented in a coroutine. And the speed of this animation is something that maybe we want our consumer to be able to control, so they can choose how quick or how fast or how slow the animation's going. So if you have kind of this animation state and you have your launch effect coroutine running that's constantly incrementing this, take that, wrap it up in an API, tack a canvas underneath, And what you have is basically a replacement for your canvas. But this time, it's basically a canvas with a draw loop. And when we do something like this, we want to make sure that we pass that animated time value to the caller that's providing the drawing commands, so that they can use the time value and incorporate it into their drawing commands. So if we were to go back to our grid and take our canvas and instead swap out the canvas for the sketch function, we immediately get access to this time variable. So if we were to take this time variable, multiply it by some coefficient, and then just insert it into one of our sine map radius transformations, we would immediately get an animation. And this is similar to one of the transformations we saw earlier. It's just changing the radius based on the sine function, but this time we're introducing a time component in it as well, and that's what's causing the animation. To make things even more interesting, we can incorporate randomness into how things are moving and changing. So in this example, we're just going to remember some random numbers, and then for every dot we draw, we're going to incorporate that random number into the sine transformation. So this means that the dots that are growing and shrinking are all growing and shrinking at different times and in slightly different ways, as specified by that random attribute. And randomness is fun, but it's too unpredictable. We can only go so far with random numbers and random number generators. And if we wanted to create some more interesting patterns or something maybe the human eye can recognize, we can't really rely on random. On the other hand, the trig functions are too predictable. We know exactly what they're going to do, so we can only go so far with those. But what if there was something that kind of fell somewhere in the middle, something a little more interesting, something more coherent than randomness, but less predictable than sine and cosine? And this takes us into my favorite topic, noise functions. Noise functions are special algorithms or special mathematical functions that produce coherent or smooth randomness. And if you give some inputs to a noise function, you're going to get the same outputs for those inputs. And most noise functions have a value that falls somewhere between -1 and 1. And every value that is produced by a noise function is similar to its surrounding value, which is what creates this smoothness. So if you look at the random distribution, which is just a bunch of like spiky points, the noise distribution is smoother. But noise functions are insanely complex. They're like 2,000, 3,000 lines of code. You don't want to write them by hand. You want to use something that's probably already out there, someone has already built. So while I was looking for something, or a library or something like that, that I could use these noise functions with, I came across this amazing library called GLM. And it is the screensaver Kotlin port of OpenGLMath. And OpenGLMath is basically what you would use for some crazy graphics programming and things like that. But this library can be used for basically any type of situation where you need a math library or a reliable math library and you need to handle vectors and matrices and things like that. So it also contains some cool functions for randomness and noise. And if you want to use GLM in your project, you're going to have to add a little extra Maven entry, and of course add your dependency as usual. So Kotlin Graphics GLM contains two different kinds of noise functions. The first one is a popular function, and some of you might have heard of this. It's called Perlin noise. Perlin noise was developed by Ken Perlin in 1983 for the original Tron movie, for which he won the Academy Award for his special effects. And 20 years later, almost, he came up with simplex noise, which was supposed to be an improvement on Perlin noise. So here's an example of like what Perlin noise looks like next to simplex. And simplex was meant to be have less artifacts and have way less computational overhead than its predecessor. And simplex kind of also looks more like TV static, or noise as you would kind of think of it, than Perlin does. So both of these functions exist in the GLM library, but they have several overloads. The first overload takes in a The first overload takes in a vector of 2 items. So a 2-dimensional vector where you pass in x and y values. So you can kind of think of 2D noise as this giant xy plane where any point in that xy plane has a noise value, and then points around that have similar values. So this is essentially how you would visualize 2D noise. The other 2 overloads are for 3rd and 4th dimensional noise. And this doesn't mean that we're actually like rendering in 3D or anything like that. It just means that there are 2 extra slots where we can plug in values that can change noise over time. So if you think of 2D noise as like a slice of an xy plane of noise, if you have more slices over time, you're going to get this animated noise, kind of like TV static. And that's basically your 3rd dimension of time going through different xy slices of noise. And don't be scared by the 4th dimension. It can also be used to animate noise with time. All right, so we can use our simple 2D noise, and instead of the random dot sizes, we can maybe use the noise function to influence our dot size. So noise is an output range of -1 to 1. And if we were to change our radius with noise, we can use our map function to convert that to some random range that we choose. And if you start doing this and try this with different coefficients and things like that, you will notice that you'll get this like really cool, almost like patterned gradient effect. And as you change the number of dots and things like that, things will start to vary a little bit. So if you compare noise to randomness, this is what your xy plane kind of ends up looking like. And you can immediately see how much more smoother the noise functions are compared to random, which is by design random. But noise functions, because of the kind of patterns they produce, can be visualized in a lot of different ways. So here we're using dots to visualize noise functions, but we can also kind of use lines to visualize the same thing. If we took our dot and instead of a dot, drew a line and oriented that line at a particular angle depending on its noise value, we would get something that looks a bit like a fluid, flowy, magnetic field type thing. These patterns are called flow fields, and they're basically a representation of noise where you slant your line at a particular angle depending on the noise value for that line. And again, when you tweak the kinds of qualities of the lines that you're drawing, flow fields can lend a very organic, cloth-like visual quality and a kind of reminiscent of magnetic fields when you have iron filings around them. So if we were to replace our dots, our circles, with lines, we need to talk about how to draw lines. Lines have 2 points, where you start and where you end. We know where we're going to start. We're going to start at wherever that dot was. But we need to figure out where the end point of our line should be. And our line is going to be slanted at a particular angle. So we need to kind of figure out where that end point of the line should be based on how much we're rotating the line. And here's another galaxy. So in order to do that, rotations and things, maybe typically you would think of rotating the whole canvas, drawing something, restoring the canvas, doing it over again, but that can get really crazy if you have just like hundreds of lines that you're trying to draw. So there should be another way of figuring out where the line should end up. And that takes us to fun high school math, polar coordinate transformations. So if this is something that probably most of us are familiar with, in order to figure out where the line should end up, given a certain angle, we return to our trig friends. And because we know where our line is starting, we can calculate where our line should end up, given a certain angle. And typically with such transformations, we're dealing in radians, not in degrees. So you're almost going to have to deal with pi in some shape or form. So we can use this sort of polar coordinate transformation for estimating where our line should end up. So if we do that, let's say we hard-code our angle at 45 degrees, or pi by 4, and we can finally get our lines kind of slanted at 45 degrees using the transformations. Now, if we just replace this hard-coded degree with a degree influenced by the noise function, we get something that looks like this. What we're doing is we're using the 2D noise function, getting a noise value that falls somewhere between -1 and 1, and then multiplying that by all the angles ever, which is 360 degrees or 2 pi, and using that to estimate where a line should end up. So if you vary the number of lines you're drawing, and if you kind of squint your eyes a little bit, it kind of looks like it's coming at you. It kind of almost has this like weird 3D quality to it. But we have flow fields. Can we animate them? That would be the next logical step. Unfortunately, animating flow fields or animating noise isn't as simple as animating trig functions. For 2D noise, we only have 2 values that we can use. Where do we plug in the time value? Or how do we kind of make the noise move forward in time? And this kind of brings us back to the higher dimension noise functions that we kind of talked about, 3D and the 4D noise. So if you use the 3D or the 4D noise, you have 2 extra slots that you can plug time values into, and then you can basically get noise animating through time. So let's try that out. When we're doing flow field animations with higher dimensional noise functions, we want things to be periodic. We want things to kind of look seamless or kind of loop or just flow from one part of the noise area to another and not look janky. And in order to accomplish anything that's smooth or repetitive, we return to our trig functions that are naturally periodic. So what we're doing here is our third and fourth dimensions of time are getting influenced by a cosine and a sine. And the cosine and sine are in turn calculated using the time variable from our sketch function. And what this does is these 2 extra dimensions are basically moving the noise values through time. And because it's a combination of cosine and sine, we're basically getting a looped noise. So it doesn't look like it's kind of just moving weirdly from one thing to another. This GIF isn't a perfect loop, that's why you see it going a little jank. But if you kind of were to just look at this on a screen, it would just endlessly flow, and it kind of looks like fur and like wind blowing through fur or something like that. So this stuff is pretty fun. So we've been working in black and white all this time, and let's see if we can add some color. With creative coding and generative art, the best way to add color is to use the hue-based color factories. And this is super useful because hue values go from 0 to 360, kind of like angles, kind of like a circle. So if you're used to representing things in terms of angles, it isn't a far cry to represent them in terms of hues as well, because they go in the same range. So in this first example, we're going to use the noise value to influence the hue, and we're going to take a fraction of all the hues ever, which is from 0 to 360 degrees based on the noise value. And because we're kind of sampling from this huge range of 0 to 360 degrees or 360 hues, we're going to see that the noise field kind of moves through sort of this rainbow of colors. The other way we could do it is we could shorten our range of how much hue we're trying to get at by using the map function. And we can just map our noise value into more screensaver, map our noise value to a small subset of hues, so we can get something that basically falls between like a purple to blue range or things like that. And this can be handy if you want to create something that's kind of just like a pretty gradient thing that falls within a certain subset of hues. All right, so this kind of rounds up the grid-based part of this. And I felt like no creative coding talk would be complete without kind of touching upon shaders at least a little bit. And shaders are a tool that a lot of generative artists use for creative coding and for generative art. And Android 13 has some fun new support for programmable shaders. So what are shaders? All right, cool. All right, shaders are programs that map a pixel's position to a color. And I'm going to skip over because we're over time. But here's an example of a shader. So people produce some crazy things with shaders. Android 13 has a cool new addition where you can use runtime shaders. So you can basically copy-paste shader code and run it on your Android device. I'm going to skip over this, but this is just a comparison of GLSL and the shading language that you will use for Android shaders. So there are 2 kinds of input values that you will need to provide your shaders. And you can get both of them using the sketch function. The first thing you'll need is a resolution or the bounds of your viewport, and the second thing you will need is a time value to animate your shaders with. Shaders are crazy complicated. Here's kind of like a 5-step thing that I use to familiarize myself with shaders. And I'm going to skip over this because some of these resources are in the last slide. All right. Okay, roundup of everything we talked about. Take your forms, use math, do crazy stuff, incorporate time. And think of inputs and outputs. So drag offsets, accelerometer things, audio levels. Use that, map it to different values, and influence the color, size, position, visual qualities of your work. And that's it. Sorry for the rushed ending, but thank you so much.